Section 11.5, expected value. Expected value. If a random variable x assumes the values x1, x2, continuing to xn, with probabilities p sub 1, p sub 2, continuing to p sub n, the expected value of x is written as e of x, which is equal to x1 times the probability of x1 plus x2 times the probability of x2 plus x sub 3 times the probability of x sub 3, continuing to x sub n times the probability of x sub n. It's the sum of the products of the values and the probabilities. Example 1. A family plans to have 4 children. Find the expected number of boys. The sample space for the family having 4 boys is, you can make the tree diagram and write all the possible combinations. 4 girls, 3 girls and a boy, 2 girls and a boy and a girl, continuing on, all the different combinations. There are 16 of them. Organizing that information into a table then. The number of boys is either 0, 1, 2, 3, or 4. The probability of each of 0 boys is 1/6. The probability of 1 boy is 4/16. 0 boys is 1/16. Probability of 2 boys is 2/16. Probability of 3 boys is 4/16. And the probability of 4 boys is 1/16. Then find the products. 0 times 1/16, 1 times 4/16, 2 times 6/16, 3 times 4/16, and 4 times 1/16. Notice I did not simplify these fractions after I multiplied, because remember, we're going to find the sum. When we're finding the sum of fractions, we want common denominators, so I did not reduce. The expected value is the sum of 0 plus 4/16 plus 12/16 plus 12/16 plus 4. 32 over 16, which is 2. Boys and girls are equally likely, so 2 of the children are expected to be boys. Example 2. A player pays $3 to play the following game. 3 coins are tossed. The game pays $1 if no heads appear, $2 if 1 head comes up, $3 if 2 heads appear, and $4 if 3 heads appear. Find the player's expected net winnings. The net winnings are how much they how much they earn after they paid $3 to play the game. Organizing our information into a chart, first we'll start with our sample space. We're flipping 3 coins. There are 8 possible outcomes. And organizing our information, our number of heads is either going to be 0, 1, 2, or 3. If there are 0 heads, you get $1. 1 head, $2. 2 heads, $3. 3 heads, $4. Net winnings. If there are 0 heads, you lose $2 because you paid $3 to play the game. 1 head, you only lose $1. 2 heads, you break even. And 3 heads, you win $1. Probabilities of our heads. Probability of 0 heads is 1/8. Probability of 1 head is 3/8. Probability of 2 heads is 3/8. And the probability of 3 heads is 1/8. Multiplying our net winnings times our probabilities. Negative 2/8 times negative 3/8 times 0 times 1/8. Our expected value, we are going to add those products. Again, common denominator is 8. They sum to negative 4/8, which is negative 0.5. The player can expect to lose 50 cents each time he plays. Example 3. How much should the player pay to play the game in example 2 to have an even chance of recovering his or her money? If it's an even chance, it means it's a fair game. In example 2, we computed that paying $3 resulted in a 50-cent expected loss. That means the cost of the game was 50 cents too high for it to be a fair game. $3 minus that 50 cents, a cost of $2.50 to play the game, makes it a fair game. Example 4. In a certain state lottery, a player pays $1 to play the daily number game. The player chooses 3 digits from 0 to 9 in a specific order. Leading zeros are allowed. The lottery operator randomly selects 3 digits. If the player's number matches, the player wins $600. Otherwise, he or she loses. Find the expected net winnings. So the probability of winning. Your first digit has a probability of 1/10. Second digit has a probability of 1/10. Third digit has a probability of 1/10. 1/10 times 1/10 times 1/10 equals 1/1000. Probability of not winning is 1 minus the probability of winning, which is 1 minus 1 over 1,000, which is 999 over 1,000. Remember that it costs $1 to play. The expected net winnings. 600 minus 1 times 1 over 1,000 plus 0 minus 1 times 999 over 1,000. 600 minus 1, well, you would win $599 because you paid $1 to play. Or 0 minus 1, you won nothing, and now you took away $1. Multiplying, it's 0.599 times negative 0.4, 0.199. A player can expect to win 20 cents. Example 5. A roulette wheel has 18 black, 18 red, and 2 white compartments. The player places a $1 bet on black or red. If the player's color comes up, he or she wins $2. Otherwise, the player loses the bet. Find the expected net winnings. There are 18 black spaces, 18 red spaces, and 2 white spaces. Expected net winnings if the player chooses black or red. He's placing a $1 bet on 18 out of 38 spaces. He would lose $1 on 18 out of 38 spaces, and he would lose $1 on 2 out of 38 spaces. Multiplying and adding, it's negative 1/19, which is negative 0.05. The expected net loss is 5 cents. expect to lose about 5 cents per play. Example 8. Take your time, read it, and organize the information in a table. Okay. Mike wishes to purchase a rail car load of lumber. 22% of the carload is 2x8 lumber, 33% is 2x10 lumber, and 45% is 2x12 lumber. Assuming a buyer selects lumber at random, the probabilities that he selects a board of a particular size is 0.22, 0.33, and 0.45 respectively. A 2x8 board retails for $10, a 2x10 board retails for $9, and a 2x12 board retails for $8. On average, how much can Mike afford to pay the wholesaler per board if he wishes to realize a profit of $3 per board sold? Again, organizing the information in a chart. The expected income is $10, $9, and $8 per board. The probability is 0.22, 0.33, and 0.45. And then find the products: $2.20, $2.97, $3.60. Your expected revenue is $2.20 plus $2.97 plus $3.60, which is $8.77. Mike wants an expected value of $3 per board sold. And let's remember that profit equals revenue minus cost. Expected profit equals expected revenue minus the cost. $3 is the expected profit per board. The expected revenue is $8.77 minus the cost. Cost equals 8.77 minus 3. Cost is $5.77. So Mike can pay up to $5.77 per board and still maintain an expected profit of at least $3 per board. That's section 11.5, expected value.